What if you could step into a machine, press a button, and wake up 100 years in the past or the future? For generations, this has been one of humanity's greatest dreams, lighting up our movie screens in films like Back to the Future and Interstellar. We've all imagined what we'd do with that power. But beyond the movies, beyond the fiction, could time travel ever really happen? To find out, we have to journey into the deepest realms of physics, from Einstein's relativity to mind-bending paradoxes and theoretical structures called wormholes. Is it just a fantasy, or does the universe hold a secret pathway through time itself? First, we need to ask a fundamental question. What is time, really? We often think of it as a constant, ticking forward at a steady pace for everyone. But Albert Einstein completely revolutionized our understanding. He showed us that time isn't separate from space. Instead, they are woven together into a single, four-dimensional fabric called space-time. Think of the universe as a giant, flexible sheet. Massive objects like stars and planets don't just sit on this fabric, they create curves and dips in it. This curvature is what we experience as gravity. So, to travel through time, we'd need to do more than just build a fast ship. We'd have to find a way to manipulate, twist, or create a shortcut through the very fabric of space-time, a challenge far beyond anything we can yet imagine, let alone engineer. But here's a surprising twist. Science says we are all time travelers, at least in one direction. Traveling to the future isn't just possible, it's already happening. This is thanks to Einstein's special theory of relativity, which reveals a strange relationship between speed and time. The faster you move through space, the slower you move through time. Imagine an astronaut taking a long journey in a spaceship, traveling near the speed of light. For them, maybe only a few years pass. But when they return to Earth, they'd find that decades or even centuries have gone by. Everyone they knew would be long gone. This isn't just a theory. We have real-world proof. Atomic clocks, which are incredibly precise, have been flown on fast-moving jets. When they land, they are ever so slightly behind the clocks that stayed on the ground. The difference is minuscule, just a few nanoseconds, but it's there. So yes, forward time travel isn't science fiction, it's physics. The only problem is that doing it on a human scale would require unimaginable amounts of energy. All right, so going forward is on the table. But what about the ultimate prize? Traveling to the past. This is where things get truly strange, and the science moves from the proven to the deeply theoretical. Einstein's general theory of relativity, which deals with gravity, does contain some peculiar mathematical solutions that allow for something called closed timelike curves. These are essentially paths through space-time that loop back on themselves, theoretically allowing an object to return to its own past. How could such a path exist? Physicists have proposed a few wild ideas. One is a wormhole, also known as an Einstein-Rosen bridge. This would be like a tunnel connecting two different points in space-time, a cosmic shortcut. Another idea involves cosmic strings, hypothetical, incredibly dense, and thin defects in the fabric of space-time left over from the early universe. If two such strings moved past each other at nearly the speed of light, they could warp space-time in a way that might permit backward time travel. But each of these ideas faces seemingly impossible challenges. Creating and stabilizing a wormhole, for instance, would require a type of exotic matter with negative energy, something we've never observed and aren't even sure can exist. It seems that even if the math works on paper, nature might have laws that forbid it in reality. And perhaps there's a very good reason for that. Let's talk about the most famous problem of all, the grandfather paradox. It goes like this. If you could travel to the past and prevent your grandparents from ever meeting, you would never have been born. But if you were never born, how could you have gone back in time to stop them in the first place? It's a contradiction that seems to make a mockery of cause and effect. This has led some physicists to propose the Novikov self-consistency principle. This idea suggests that the universe has a built-in protection mechanism. It states that any event that would create a paradox is simply impossible. The laws of physics would conspire to prevent it. For example, you might go back in time to stop an event, but your actions, no matter what you do, would accidentally become the very thing that causes the event to happen. Time, in this view, is robust and self-correcting. You can't change the past because you are already part of it. But what if the past isn't set in stone? There's another fascinating and perhaps even stranger solution to the paradox problem: the multiverse. Drawing from interpretations of quantum mechanics like the many worlds theory, this idea suggests that every time you make a decision or every time a quantum event has multiple possible outcomes, the universe splits into parallel realities. So, if you traveled to the past to stop your grandparents from meeting, you wouldn't be changing your timeline. Instead, your arrival would create a new, branching timeline, one where you don't exist. Your original universe, the one you came from, would remain completely untouched. You would simply be stuck in a new one of your own making. This neatly resolves all paradoxes, but it opens up a whole new can of worms. If there are infinite versions of reality, which one is the real you? It's a mind-boggling concept that pushes the boundaries of both physics and philosophy. So, if we were to look for a natural time machine, where in the universe would we find one? If time travel is possible anywhere, it's near the universe's most extreme and violent objects, black holes and wormholes. As we mentioned, wormholes could theoretically connect two distant points in both space and time. Physicists like Kip Thorne have done serious work on this, theorizing that a sufficiently advanced civilization could potentially capture a wormhole and stabilize it with that exotic negative energy matter. You could then take one end of the wormhole on a high-speed journey and bring it back. Because of time dilation, the two ends would now exist in different time periods. Step through one way, you go to the future. Step through the other, you go to the past. And then there are black holes. The gravity around a black hole is so intense that it warps space-time to an unimaginable degree. Time slows down dramatically near its edge, the event horizon. If you could orbit a supermassive black hole for just a few minutes, you could return to your starting point to find that years, or even millennia, have passed elsewhere in the universe. It's the ultimate form of one-way travel to the future. With all these mind-bending possibilities, we have to ask a simple question. Why does time seem to only move forward for us? Why do we remember the past but not the future? The answer might lie in a concept called the arrow of time, and it's tied to one of the most fundamental laws of physics, the second law of thermodynamics. This law describes entropy, which is essentially the universe's tendency to move from order to chaos. A glass can shatter into 1,000 pieces, but we never see the pieces spontaneously reassemble into a glass. An egg can be scrambled, but not unscrambled. This constant increase in disorder gives time its direction. It separates cause from effect. Almost every other law of physics works just as well forward as it does backward, but entropy doesn't. This thermodynamic arrow of time is what gives us our sense of past, present, and future. If we could ever figure out how to locally reverse entropy, to turn chaos back into order, perhaps time itself would bend with it. So, will we ever crack these cosmic codes? Interestingly, our most powerful new tool in this quest might not be a bigger telescope or a faster particle accelerator, but artificial intelligence. AI is now being used by physicists to run incredibly complex simulations of quantum systems and space-time geometries. Machine learning algorithms can explore the dynamics of wormholes, model the effects of extreme time dilation, and search for patterns in cosmic data that human brains might miss. We might not build a physical time machine in our lifetimes, but through these advanced simulations, AI could help us build a virtual one. It could allow us to explore the consequences of time travel and test the limits of physical law, all from the safety of a computer. In the end, our fascination with time travel isn't just about the thrill of escaping the present or fixing the mistakes of the past. It's about a deep human desire to understand our place in the cosmos. It's about confronting the nature of our own existence, the fact that we are temporary beings living in a universe of constant change. Time gives our lives meaning. It reminds us that our moments are precious, that everything changes, and that our curiosity to understand it all is what truly endures. Perhaps the real time machine isn't a device built of metal and wires, but the one we all carry inside us, the human mind, capable of traveling through memory to the past and through imagination into the future. Thanks so much for exploring this incredible topic with us today. If you enjoyed this journey through space-time, make sure to hit that like button, subscribe to the channel, and ring the bell so you don't miss our next adventure. Until next time, stay curious.